Today we are going to learn about optimizing Scikit-learn Random Forest for performance. We'll explore key hyperparameters and best practices for tuning them to enhance model efficiency and accuracy.
Welcome to our video on optimizing Scikit-learn Random Forest for performance. Random Forest is a versatile and widely used machine learning algorithm that builds multiple decision trees and merges them together to get more accurate and stable predictions. In this video, we'll delve into the world of hyperparameters, which are crucial in determining the performance of your model. These hyperparameters control various aspects of the algorithm, from the number of trees in the forest to the depth of each tree. By understanding and fine-tuning these parameters, we can significantly improve the accuracy and efficiency of our models. So, let's get started and explore the key hyperparameters of Random Forest. Hyperparameter tuning is a critical step in building any machine learning model, particularly when using complex algorithms like Random Forest. The process of tuning involves selecting the best set of parameters that lead to the highest model performance. Without proper tuning, your model might either overfit or underfit the data. Overfitting occurs when the model learns the noise in the training data, leading to poor generalization to new data. Underfitting, on the other hand, means the model is too simple and fails to capture the underlying patterns. By optimizing hyperparameters, you can achieve a balance between bias and variance, leading to a more robust and reliable model. Additionally, tuning improves computational efficiency by reducing unnecessary complexity, making it faster to train and execute. In essence, hyperparameter tuning is the key to unlocking the full potential of your random forest model. The max_depth parameter in a random forest determines the maximum depth of each decision tree. This hyperparameter plays a crucial role in controlling the complexity of the model. A deeper tree can model more complex patterns in the data, but it also risks overfitting. On the other hand, a shallow tree might not capture enough information, leading to underfitting. To find the optimal max_depth, you can experiment with different values using cross-validation to assess how each setting affects the model's performance. Generally, starting with a smaller max_depth and gradually increasing it can help in identifying the sweet spot where the model performs best on unseen data. Let's consider an example. If your initial model with a max_depth of 10 shows signs of overfitting, you might reduce it to 5 or 7 and observe improvements in cross-validation scores. Understanding and adjusting max_depth is crucial for optimizing the balance between capturing intricate patterns and maintaining generalizability. The max_features parameter specifies the number of features to consider when looking for the best split in each tree. This parameter has a significant impact on the diversity of the trees in the forest. By limiting the number of features, you introduce randomness, which helps in reducing the correlation between the trees and thus enhances the robustness of the model. However, setting max_features too low might lead to high bias, while too many features can increase variance and computational cost. Common strategies include using the square root of the total number of features for classification tasks and the logarithm for regression tasks. For example, if you have a dataset with 100 features, setting max_features to the square root of 100, which is 10, might be a good starting point. Experimentation and cross-validation are crucial in determining the optimal value. By fine-tuning max_features, you can achieve a balance between diversity in the ensemble and the computational efficiency of the model. The n_estimators parameter is another critical hyperparameter in Random Forest, representing the number of trees in the forest. The more trees, the better the model's performance tends to be, as it reduces variance and improves predictive accuracy. However, more trees also mean longer training times and increased computational costs. It's essential to find a balance where adding more trees doesn't significantly improve the model's performance. Typically, starting with a value of 100 trees and gradually increasing can help determine the optimal number. Monitoring the out-of-bag error or using cross-validation can guide this process. By carefully tuning the n_estimators parameter, you can enhance model accuracy while maintaining reasonable training times.
Grid search is a powerful tool in Scikit-learn for hyperparameter tuning. It automates the process of evaluating a model on all possible combinations of a specified parameter grid, using cross-validation to assess performance. This approach ensures a comprehensive search, increasing the likelihood of finding the optimal hyperparameters for your model. To use grid search, define a parameter grid with the ranges of hyperparameters you wish to explore. For example, you might specify ranges for max_depth, max_features, and n_estimators. Then, initialize the grid search object with your model, the parameter grid, and the desired cross-validation strategy. After fitting the model, grid search provides the best combination of hyperparameters and their corresponding performance metrics. This systematic approach is invaluable for ensuring your random forest model is fine-tuned for optimal performance, saving time and improving accuracy.
Balancing overfitting and underfitting is a common challenge in machine learning. Overfitting occurs when the model learns the noise and details of the training data, performing well on it but poorly on unseen data. Underfitting happens when the model is too simple, failing to capture the underlying patterns in the data. To achieve a balance, careful tuning of hyperparameters is essential. Using cross-validation allows you to evaluate how different hyperparameter settings perform on various subsets of the data, helping identify overfitting or underfitting tendencies. Adjusting parameters like max_depth, max_features, and n_estimators can help achieve this balance. For instance, reducing max_depth may prevent overfitting, while increasing n_estimators can improve accuracy without increasing variance significantly. Finding the right balance ensures your random forest model generalizes well, providing reliable predictions on new data. Let's explore real-world examples of hyperparameter tuning in random forest. In a healthcare setting, random forest can be used for predicting patient outcomes based on a variety of clinical features. By carefully tuning hyperparameters, such as max_depth and n_estimators, practitioners have improved the model's predictive accuracy, leading to better patient management strategies. In finance, random forest models are employed for credit scoring, where tuning hyperparameters has resulted in more precise risk assessments, reducing default rates. These examples highlight the importance of hyperparameter tuning in achieving reliable and effective models. The lessons learned from these cases emphasize the need for a systematic approach, using tools like grid search and cross-validation to explore different configurations. By adopting best practices, you can enhance the performance of random forest models across various domains, delivering significant value and insights. To ensure efficient model training, it's essential to follow best practices in hyperparameter tuning. Start with default settings and establish a baseline performance. Use cross-validation to evaluate the model's performance on different subsets of data, identifying areas for improvement. An iterative approach, where you gradually adjust one hyperparameter at a time, can help in understanding the impact of each setting. Monitor performance metrics closely, such as accuracy, precision, and recall, to guide your tuning process. Additionally, leverage computational resources effectively by using parallel processing or cloud services to speed up the training process. By following these best practices, you can ensure your random forest model is both efficient and effective, delivering high-quality predictions in a reasonable timeframe. In conclusion, mastering the optimization of random forest models is an essential skill for data scientists and machine learning engineers. We've covered key hyperparameters like max_depth, max_features, and n_estimators, and explored tools like grid search for effective tuning. By understanding the balance between overfitting and underfitting and applying best practices, you can significantly enhance your model's performance. Real-world examples demonstrate the profound impact of these techniques across various fields. Now, it's time to apply what you've learned. Experiment with different settings, utilize cross-validation, and practice tuning on diverse datasets to hone your skills and become proficient in optimizing random forest models for exceptional performance.